In August 1943, at the Quebec Conference, a British officer stood before a room of the most powerful military minds in the Allied command. He raised his service pistol and fired at a block of ice. It shattered into fragments across the floor. The admirals and generals watched, unimpressed. Then he aimed at a second block, one that looked identical to the first, and pulled the trigger again. The bullet ricocheted off the surface, buzzing past the legs of Admiral Ernest King, Commander-in-Chief of the United States Fleet, before embedding itself in the wall behind him. This wasn't ice. This was something the Germans would never see coming. By the time this conference ended, the Allies would be racing to build the largest ship ever conceived, a 2,000-foot aircraft carrier made from frozen water and wood pulp that would be virtually indestructible, unsinkable, and capable of carrying 300 bombers into the heart of the Atlantic. And for a brief, extraordinary moment in 1943, it was actually going to happen. But what you're about to hear isn't a story of triumph. It's the story of how Britain's most ambitious secret weapon, one that terrified German intelligence when rumors reached them, one that Winston Churchill championed personally, one that a future Nobel Prize winner helped engineer, became the most spectacular engineering failure of World War II. This is the story of Project Habakkuk and why the laws of physics proved more formidable than any U-boat. The material that nearly ricocheted a bullet into Admiral King's chest was called pykrete, and understanding it requires understanding why Britain was desperate enough to freeze sawdust into warships in the first place. By 1942, German U-boats were winning the Battle of the Atlantic. They were sinking Allied ships faster than they could be replaced. The mathematics were simple and brutal. Every week, dozens of cargo vessels carrying food, fuel, and war materials from North America were being torpedoed and sent to the bottom of the ocean. Britain was starving. The Royal Navy needed air cover over the Atlantic convoys, but aircraft carriers required massive amounts of steel that was already in catastrophic shortage. Geoffrey Pike had a solution. Pike was a British inventor and journalist who'd spent World War I escaping from a German prison camp and the interwar years making a fortune in commodities trading while rarely showering and calling most people around him buffoons. He was, by all accounts, brilliant and insufferable in equal measure. In 1942, while working for Britain's Combined Operations Headquarters, he realized something elegant. Water freezes. Water is free. Ice floats. Therefore, aircraft carriers could be made from ice. The initial concept was almost childlike in its simplicity. Tow a giant iceberg from the Arctic, flatten the top, hollow out the interior for aircraft storage, and deploy it into the Atlantic. But the plan immediately hit reality. Natural icebergs have 90% of their mass underwater. To maintain 50 feet of freeboard, the minimum height above water needed for aircraft operations, you'd need 500 feet of ice below the surface. That much draft would make the ship impossible to maneuver and keep it out of most harbors. Worse, icebergs are fundamentally unstable. They flip without warning as their weight distribution shifts during melting. You cannot land a bomber on a runway that might suddenly capsize, so Pike pivoted to construction, build the carrier from blocks of ice instead. But pure ice presented another problem that would have killed the project immediately. Ice is brittle. Ice deforms under pressure through a process called plastic flow. It sags and bends under its own weight like extremely slow-moving honey. Any ship large enough to serve as an aircraft carrier would, as Pike himself admitted, slowly sag under its own weight until it resembled a melting sculpture more than a warship. This is where Max Perutz entered the story. Perutz was a molecular biologist and glacial expert who would later win the Nobel Prize in chemistry. In early 1942, Pike and his colleague J.D. Bernal brought Perutz into the project to solve the ice problem. Perutz was conducting his experiments in the most absurd location imaginable, a refrigerated meat locker beneath Smithfield Market in London, hidden behind walls of frozen animal carcasses to maintain secrecy. There, he tested various ice compositions, looking for something that would retain ice's buoyancy and ease of production while solving its structural weaknesses. The breakthrough had actually already been made. Perutz just had to find it. two American researchers, Mark and Hohenstein, had published a paper describing experiments with frozen wood pulp. When water was mixed with sawdust or wood pulp and then frozen, the resulting composite material was radically different from pure ice. The wood fibers interrupted the crystalline structure, preventing the kind of catastrophic fracturing that made ice so brittle. Perutz refined their formula through systematic testing. The optimal ratio was 14% sawdust to 86% water. This material, dubbed pykrete after Geoffrey Pike, was 14 times stronger than pure ice. It resisted compression, it resisted chipping, and most remarkably, it could stop bullets. The mechanism behind pykrete's bullet resistance reveals why it seems so promising. When a projectile strikes pure ice, it transfers kinetic energy into the crystalline matrix, which shatters along its natural fracture planes, but pykrete's wood fibers absorb and distribute that impact energy across a three-dimensional network. The bullet's force dissipates into the composite structure instead of propagating through crystal planes. Additionally, when pykrete was immersed in water, as it would be on the exterior of a hull, the wood fibers at the surface absorbed moisture and formed a protective layer of wet pulp that dramatically slowed interior melting. The material essentially created its own insulation, but Perutz discovered a critical limitation that would ultimately doom the entire project. Pykrete only maintained its structural integrity below -16 degrees Celsius. That's 3 degrees Fahrenheit. Above that temperature, the ice component began to exhibit plastic flow despite the wood fiber reinforcement. The ship would still sag under its own weight unless it was kept frozen through active refrigeration. This meant the entire vessel would need to be wrapped in insulation and laced with a complex network of refrigeration piping carrying chilled brine through every section of the hull to maintain structural integrity. You couldn't just build a ship from pykrete and sail it. You had to build a ship from pykrete and then build a massive industrial refrigeration plant inside it to keep it frozen. Lord Louis Mountbatten, Chief of Combined Operations and a member of the British royal family, became Habakkuk's most powerful champion. Mountbatten had a weakness for unconventional ideas and unconventional people, and Pike qualified on both counts. According to one account, Mountbatten once burst into Winston Churchill's bathroom while the Prime Minister was taking a bath and dropped a block of pykrete into the hot water to demonstrate how slowly it melted compared to pure ice. Churchill watched the block float, its outer layer gradually dissolving while the interior remained solid. The Prime Minister was sold. He gave the project his personal backing and the highest priority designation. The design that emerged from Combined Operations Headquarters was staggering in its ambition. The final specifications for Habakkuk II called for a vessel 600 meters long, nearly 2,000 feet, and 200 meters wide. The hull would be 40 feet thick to provide torpedo protection. The ship would displace 2.2 million tons, making it the largest mobile structure ever conceived by human beings. For comparison, the USS Enterprise, the largest aircraft carrier in the modern U.S. Navy, displaces about 100,000 tons. Habakkuk would be 22 times heavier. The internal layout was equally ambitious. 2 enormous hangars would run the length of the ship's interior, capable of housing up to 150 twin-engine bombers or 300 fighter aircraft. The flight deck would be 2,000 feet long to accommodate heavy bomber takeoffs. The vessel would be armed with 40 dual-barreled 4.5-inch gun turrets for surface defense, plus numerous anti-aircraft batteries. For propulsion, steam turbo generators would produce 33,000 horsepower to drive 26 electric motors housed in external nacelles along the hull. The motors had to be external because normal internal ship engines would generate too much waste heat and melt the pykrete structure from the inside. Steering presented an unsolved nightmare. The initial plan was to navigate by varying motor speeds on either side of the vessel, essentially tank steering. But the Royal Navy insisted on a proper rudder for precise maneuvering. Nobody could figure out how to mount and control a rudder over 100 feet tall that would be pushing against millions of tons of ship. The problem was never solved before the project ended. In 1943, Canada became the testing ground for Habakkuk. The National Research Council of Canada was assigned the project because of Canada's cold winters, abundant fresh water, cheap wood pulp, and available labor. Lake Patricia in Jasper National Park, Alberta, was selected as the construction site. The location was remote, close to a conscientious objectors camp that provided labor, and cold enough to maintain ice through most of the year. The prototype built on Patricia Lake was a scale model, 60 feet long, 30 feet wide, weighing 1,000 tons. It was shaped like a shoebox and kept frozen by a single 1-horsepower motor driving the refrigeration system. 8 men took 2 weeks to build it. The construction process involved cutting massive blocks of ice, mixing sawdust into the surface layers, and assembling them into a hull shape while refrigeration pipes were threaded through the structure. The model floated. It survived munitions tests and explosive charges. It proved that pykrete could work as a hull material, but the prototype also proved that scaling up to the full Habakkuk design would be vastly more expensive and complex than anyone had projected. The Canadians estimated that a full-size vessel would require 300,000 tons of wood pulp, 25,000 tons of fiberboard insulation, 35,000 tons of timber, and 10,000 tons of steel just for the refrigeration system and structural reinforcement. That steel requirement was the killer. Building a conventional aircraft carrier from steel required less steel than building Habakkuk's refrigeration infrastructure. The project that was supposed to save steel was consuming more steel than it would save. The cost estimate spiraled. Initial projections put each Habakkuk at 700,000 British pounds. By mid-1943, that figure had tripled to 2.5 million pounds, equivalent to roughly 150 million pounds today. And the timeline kept slipping. The Canadians determined it was impractical to attempt construction until the winter of 1944, meaning no operational vessel before 1945 at the earliest. Churchill had wanted a fleet of ice carriers ready for the 1944 invasion season. Physics and logistics were saying no. Then the strategic situation changed. In May 1943, Germany ordered its U-boats to leave the mid-North Atlantic. Allied codebreakers had cracked the Enigma cipher, allowing convoy routing that avoided Wolfpack concentrations. Portugal granted Britain access to airfields in the Azores, dramatically extending the range of anti-submarine patrols. The introduction of long-range fuel tanks gave land-based aircraft the ability to cover most of the Atlantic. And the United States was producing escort carriers, small, cheap aircraft carriers converted from cargo ship hulls at an accelerating rate. The mid-Atlantic gap that Habakkuk was designed to fill was closing through other means. At a Chiefs of Staff meeting in August 1943, naval architects presented 3 variants of the Habakkuk concept. Habakkuk I, made entirely of wood, was immediately discarded. Habakkuk II was closest to the original vision, the enormous pykrete vessel with 2 000-foot flight deck. Habakkuk III was a smaller, faster version. Air Chief Marshal Portal asked about bomb damage resistance. Bernal admitted that bomb holes in the deck could probably be patched with flexible matting, but holes in the central hangar roof would be much harder to repair despite planning for blast-proof construction. He confessed that nobody could definitively say whether Habakkuk II was practical until a large-scale model was completed and tested in Canada in spring 1944. The room was full of Britain's highest military commanders, and the man leading the project couldn't promise them it would work. The final meeting of the Habakkuk board occurred in December 1943. By that point, even Mountbatten had withdrawn his support. The official conclusion was direct. The large Habakkuk II, made of pykrete, has been found to be impractical because of the enormous production resources required and technical difficulties involved. The project was dead. But the story of why it died reveals something profound about the difference between inspired innovation and practical engineering. Habakkuk failed because Pike and his team confused a clever material discovery with a viable weapons system. Pykrete was real. It genuinely was stronger than ice, slower to melt, and resistant to projectiles. The science worked, but building a functional aircraft carrier required more than a strong hull material. It required solving hundreds of interconnected engineering challenges, and each solution created new requirements that eventually consumed more resources than conventional alternatives. Consider the refrigeration problem in detail. To keep 2.2 million tons of pykrete below -16 degrees Celsius, While floating in ocean water that could be as warm as 20 degrees Celsius in summer, you needed industrial-scale refrigeration distributed throughout the entire hull. The system required miles of piping carrying refrigerated brine, multiple power plants to drive the compressors, pumps to circulate the coolant, and insulation covering every exterior surface. The complexity rivaled the rest of the ship's systems combined, and if any section of the refrigeration system failed, if pipes burst, if pumps seized, if power was lost, that section of hull would begin melting. Once melting started, the wood pulp insulation would degrade, accelerating the process. A single torpedo hit that damaged refrigeration infrastructure could trigger a cascading structural failure that no amount of picrete strength could prevent. The wood pulp requirement created another cascade of problems. 300,000 tons of wood pulp represented a significant fraction of Canada's entire annual production. Building even a few Habakkuk carriers would severely impact paper manufacturing, printing, and cardboard production across the country for years. You'd be trading aircraft carriers for newspapers, books, and packaging materials. The military might gain sea power, while the civilian economy lost a critical industrial input. Manpower was equally prohibitive. Canadian estimates projected that producing the necessary picrete blocks would require 8,000 workers laboring for 8 months just to manufacture 280,000 individual 40-foot cubes of frozen wood pulp. Those workers would need to operate in refrigerated facilities in the dead of winter, cutting ice, mixing sawdust, freezing blocks, and transporting them to the assembly site. Then thousands more workers would be needed to assemble the blocks into a hull, install the refrigeration systems, construct the flight deck and hangars, and fit out the vessel with aircraft handling equipment, fuel systems, ammunition storage, crew quarters, and all the other infrastructure of a functioning warship. The labor pool required to build one Habakkuk could have built multiple conventional carriers with less technical risk. Navigation presented problems that were never adequately solved. Habakkuk's enormous mass meant its momentum would be immense. A 2.2 million-ton ship moving at 6 knots has roughly the same kinetic energy as a modern supertanker at full speed. Stopping such a vessel would take miles of ocean and minutes of time. Turning it would require sustained force over vast distances. The rudder solution remained theoretical. Nobody had worked out the mechanical systems required to move a 100-foot rudder against the water resistance generated by millions of tons of ship, and the alternative steering method, varying motor speed on each side, would be sluggish and imprecise. You'd have an aircraft carrier that couldn't effectively maneuver in combat, couldn't enter most ports, and couldn't quickly respond to tactical situations. The vulnerability assessment was also more complicated than Pikerete's bullet-stopping demonstration. He suggested, yes, Pikerete could stop small arms fire and resist torpedo impacts better than steel. But what happens when a 1,000-kilogram bomb penetrates 40 feet of frozen wood pulp and detonates inside the hull? The explosion would vaporize ice, shatter wood fibers, rupture refrigeration piping, and create a massive crater that would immediately begin flooding with seawater and melting. Repairing such damage would require cutting out the damaged section, fabricating new Pikerete blocks, and installing them while maintaining refrigeration in adjacent areas. You'd essentially need a floating ice factory and construction yard as part of the ship's damage control capability. No such system was ever designed. The crew habitability inside a giant frozen ship presented its own misery. Personnel would be living and working inside what was essentially a refrigerated warehouse. The interior spaces would need constant heating to remain survivable, creating a thermal management nightmare where you're simultaneously trying to keep the hull frozen and the crew compartments warm. Condensation would be endemic as warm, moist air from crew spaces met cold surfaces. Ice would form constantly on interior walls and equipment. Metal tools and machinery would become dangerously cold to touch. The working conditions would be brutal even by wartime standards. And then there was the operational range limitation. Habakkuk's refrigeration system required fuel to run continuously. The ship's power plants needed fuel for propulsion and electricity generation. Fuel storage in a frozen hull presented contamination risks as petroleum products interacted with melting ice. Refueling at sea would be complicated by the ship's low speed and poor maneuverability. The theoretical 7,000-mile range assumed optimal conditions and functioning systems. In practice, operational range would likely be much shorter, limiting where Habakkuk could effectively patrol. The Germans never faced Habakkuk in combat, but intelligence reports about Allied experiments with ice ships did reach German Naval Command. Their response was documented in post-war interrogations. They were initially baffled. The reports seemed too outlandish to be credible. But as more details filtered through intelligence networks, German analysts took the threat seriously enough to study countermeasures. Their conclusion was pragmatic. If the Allies built ice ships, Germany would target them with sustained aerial bombing rather than torpedo attacks. Bombs could deliver enough explosive force to overwhelm Pykrite's structural integrity, especially if they penetrated to the interior before detonating. The Germans recognized that Habakkuk's greatest vulnerabilities weren't its hull material but its complexity and the catastrophic consequences of any system failure. By early 1944, the small prototype on Patricia Lake had been abandoned. The 1-horsepower motor shut down. The refrigeration stopped. And then, something remarkable happened that perfectly encapsulated why Habakkuk was ultimately impractical. It took 3 hot Canadian summers for the prototype to completely melt. The wood pulp in the Pykrete slowed melting so effectively that a 1,000-ton block of frozen sawdust and water survived for nearly 3 years before finally dissolving and sinking to the lake bottom, where its metal components remain today as a destination for divers. That stubborn persistence in melting was both Pykrete's greatest strength and Habakkuk's fatal weakness. Yes, the material was extraordinarily durable and resistant to melting, but that same durability meant it required enormous energy input to create and maintain. You had to freeze millions of tons of water and sawdust to specific temperatures, then continuously pump refrigeration through the structure to prevent natural melting. The energy cost of creating and maintaining Pykrete at scale exceeded the energy cost of producing steel. Britain was trying to save resources by using ice, but ice only works as a free material when nature freezes it for you. Artificially created and maintained ice is expensive. Max Perutz, reflecting on the project after the war, was characteristically direct about why it failed. He wrote that U.S. Navy engineers concluded Habakkuk was a false prophet. The enormous amount of steel needed for the refrigeration plant exceeded the steel required to build an entire conventional carrier. But the crucial argument, Perutz noted, was that the rapidly increasing range of land-based aircraft rendered floating islands unnecessary. The strategic problem Habakkuk was meant to solve had been solved by other means before Habakkuk could be built. This is the nature of weapons development in wartime. The problem changes faster than the solution can be implemented. In 1942, the Mid-Atlantic Gap was a critical vulnerability. By 1944, it no longer existed. Habakkuk wasn't obsolete because it was a bad idea. It was obsolete because other good ideas reached operational status first. Long-range patrol aircraft, escort carriers, improved radar, Enigma decryption, and better convoy tactics collectively closed the gap that one enormous ice ship was supposed to fill. Jeffrey Pike took the project's cancellation hard. He had genuinely believed Habakkuk could change the course of the war. When it was shelved, he felt vindicated in his frequent complaint that others couldn't see what he could see. He continued proposing ambitious ideas, including a tube system attached to troop carrier ships meant to help soldiers land more safely on Japanese-held islands, but none gained traction. In February 1948, at age 54, Pike was found dead by his landlady. He had taken an entire bottle of sleeping pills. His body was lying on papers he'd been writing on. Some speculated he was working on advanced mathematical physics. Others suggested he was simply exhausted and depressed. The man who had envisioned aircraft carriers made of ice didn't live to see the jet age, nuclear propulsion, or the supercarriers that would dominate naval warfare for the rest of the century. The Americans were offered the Habakkuk concept for potential use in the Pacific theater. They declined. The U.S. Navy's analysis concluded that the steel requirements, construction timeline, and operational limitations made Habakkuk inferior to conventional carriers they were already building in large numbers. American shipyards were launching Essex-class carriers every few months by 1943. fast, steel-hulled fleet carriers that could operate globally without requiring refrigeration plants to maintain hull integrity. Why build an experimental frozen ship when proven steel ships were rolling off assembly lines? Modern attempts to recreate Pykrete boats have validated both its remarkable properties and its practical limitations. In 2009, the television show Mythbusters built a small boat from modified Pykrete using whole newspaper sheets instead of wood pulp. They successfully piloted it at 25 miles per hour in Alaskan waters, but within 20 minutes it began leaking through melting Pykrete. After 30 minutes, the pump couldn't keep up with the water intake and they had to return to shore trailing sloughed newspaper in their wake. Their conclusion: plausible but ludicrous. Pykrete worked exactly as advertised. It was strong, slow-melting, and bullet-resistant, but building a functional boat from it required constant attention to melting, active maintenance, and limited operational duration. Scale that up to a 2.2 million-ton aircraft carrier, and the ludicrous part overwhelms the plausible part. Sir Charles Goodeve, who had been Assistant Controller of Research and Development for the Admiralty during the war, published a devastating critique of Habakkuk after hostilities ended. He pointed out that building one Habakkuk would consume 40,000 tons of cork insulation, thousands of miles of steel tubing, and 4 power stations worth of generating capacity. For all those resources, many of which could have been used to manufacture conventional ships, Habakkuk would be capable of traveling at only 6 knots. That's barely faster than a brisk walk. German U-boats could do 17 knots submerged. Any surface ship could outrun Habakkuk. The carrier could launch aircraft to hunt submarines, but it couldn't chase them itself. It would be a mobile airfield, not a warship in the traditional sense. The remains at the bottom of Patricia Lake tell the final chapter of this story. Divers who visit the site find twisted metal piping, fragments of the wooden framework, and the detritus of the refrigeration system scattered across the lake bed. There's a commemorative plaque on the shoreline that identifies the location as a secret World War II project involving ice and ship construction, deliberately vague about the details even decades later. The physical evidence of Habakkuk is rust and rotting wood in cold Canadian water, a monument to the gap between ambitious vision and practical execution. But the deeper lesson of Project Habakkuk isn't about failure. It's about the nature of innovation under pressure. When Britain faced existential threat in the Atlantic, when steel was scarce and U-boats were winning, trying to build aircraft carriers from ice wasn't crazy. It was rational experimentation with alternative solutions. The Pykrete research was legitimate science. The scale model worked. The concept had merit within its narrow parameters. What killed Habakkuk wasn't flawed thinking, but the brutal arithmetic of resource allocation and the reality that engineering complexity grows exponentially with scale. Geoffrey Pike's other contributions to the war effort were substantial and successful. His screw-propelled vehicle for snow operations, the M29 Weasel, proved highly effective in the Italian campaign and became a standard vehicle for winter warfare. His intelligence surveys provided valuable information about German civilian morale. His willingness to propose unconventional solutions pushed military thinking beyond traditional boundaries. Habakkuk's failure doesn't diminish those successes. It simply demonstrates that not every bold idea can overcome physical constraints, even with unlimited political support and talented engineers. The German officers who heard rumors about Allied ice ships probably did struggle to believe what their intelligence reports described. The concept sounded like propaganda or disinformation, too absurd to be real. But it was real. Britain's most powerful leader championed it. A future Nobel laureate engineered it. Canadian workers built a prototype in a frozen lake. The physics worked. The material performed as designed, and yet it still failed, not because it was impossible, but because it was impractical at the scale required to matter militarily. That's the final irony of Project Habakkuk. The Germans didn't need to defeat it in combat. Time and physics defeated it in the laboratory and on the drafting tables. The carrier made from ice never faced a U-boat because it never made it out of Lake Patricia. The secret weapon that Churchill believed would change the war melted away before it could fight. leaving nothing behind but rust on a lake bottom and one of the strangest footnotes in military history.